In this video, we're going to talk about SADA, Semantic Adversarial Diagnostic Attacks for Autonomous Applications, the paper that is presented in AAAI 2020 in New York. In deep learning, adversarial attacks are defined as small, imperceptible noise that's added to the image to fool a trained deep network. The question is, are these adversarial attacks on the pixels meaningful? Can they help and explain the deep networks? Another thing is, are they useful for safety applications? And the answer is mostly no. Here comes the semantic adversarial attacks, in which the attacks are not performed on the pixels, but on the parameters that define the environment in which the agent lives. For example, the change can be in the camera view angle, or the geometry of the track, or even in the weather in which the self-driving car is being tested on. The main contributions of the paper is that we propose a new general setup that include conventional pixel attacks as well as the semantic adversarial attacks. We propose BBGAN, a network to learn the underlying distribution of semantic adversarial attacks. We apply it on 3 safety critical applications: object detection with YOLO version 3, self-driving car in the Carla simulator, and UAV racing in SEM4CV. We show how this BBGAN can help us get useful insights about these agents. Our proposed general setup includes an entity we call adversary, in which the interaction between the agent and the adversary is through the environment, E. So the adversary is basically trying to give an input to the environment such that the agent would fail in that environment. And then a score will be returned to adversary in order to update itself and get a better attack in the following. This setup applies to conventional pixel attacks in which the environment is just the dataset of images, and it applies also to several semantic attacks, as we will see in this paper. Here we show how BBGAN, or a GAN that tries to learn the distribution of parameters that will fool the agent in the environment. The training happens by passing a set of different parameters, and then the inducer would try to filter all of these parameters according to their Q score obtained from the environment, and then the filtered parameters would be passed to the GAN for training. After training, the BBGAN would basically sample fooling parameters that would always be fooling for the agent. Now let's show some applications. We apply our SADA framework on 3 different safety critical applications: object detection with YOLO version 3, self-driving cars in Carla simulator, and UAV autonomous racing in SEM4CV. In object detection, we define the environment parameters as the camera viewpoint, the camera distance, the light direction, and the RGB color of the object of interest. Here we show some examples from the generated images. We can see that the truck is misclassified as a laptop or a cell phone by the YOLO version 3 detector. Here we visualize the distribution of the camera view angles and the light directions that will constitute a threat to the YOLO detector if the object was car. On the left, we show a simulated image from these threat angles, how the object was misclassified as cell phone. On the right, we show how a real photo taken from the same angle as the simulated one actually result in the similar misclassification. Here we show how a trained agent works fine on Carla simulator for self-driving car. However, when the environment is attacked by our BBGAN, the agent fails, as can be seen here. Here, we show a trained agent navigating through UAV racing track. Now we generate adversarial tracks that will fool the agent, as can be seen in this case. Our BB GANs show improvement over all other baselines. You can check our paper and the code for the project in these two links. This is me and my colleagues from KAUST. Thanks for watching.